Okay, so now we're going to be moving on to testing the whether or not the slope is statistically different from zero. So this is the setup that we've got, looking very much like the things that you've seen many times before. So what are the ingredients that we need for our t-test? Well, we need a null and an alternate. They're going to be pretty simple to generate. So I've said we're going to have alpha at 0.05 again. We do need a test, formally we need a test statistic. Okay, in practice we're going to use p-values, but remember the p-value is really being derived from the distribution of the test statistic, and of course we need to apply a decision rule. This looks remarkably like what you've done time and time again. So before we jump into looking at the testing the slope in the regression coefficient, I do want to just recall what we were saying when we looked at single sample t-tests. What were we doing? We were saying we were using the sample data to infer something about the population. Okay, so we're saying we weren't actually interested in this particular sample, but we were using this sample to infer something about the population. We would say something about, is it equal to our target value? So in our case, our target value is going to be 0. But we have seen exactly this setup before with our single sample t-test. The null, the mean is not different to something. The alternate, the mean is different to something. T-test, what did we have? We had the sample mean and we had the standard error of the mean. The decision rule, p-value less than 0.05. What did we do? So the example I had was a coal company. We were doing about how much dirt we had to move to get to the coal. So we had the null, the mean is equal to 50. The alternate, the mean is not equal to 50. Loaded the data into R. And just look at the test statistic formula here. We had the sample mean, so that was the thing given from our data, minus the null hypothesis value divided by the standard error of the mean. So this is a pretty standard formula for looking at a number of tests. Okay, so there was our t-test statistic. So what did we do? We read some data into R. We looked at our data. This was testing against. We run the test, interpret the results. So we got a p-value of 0.41, so that would be above 0.05, therefore we do not reject the null. So we'd say we have insufficient evidence to reject the company's claim. Okay, so we've very much seen how this kind of test works. Now I also want to just remind you of really what's going on in this calculation. So when we have our test statistic formula, sample mean minus the null hypothesis value divided by the standard error of the mean. So we could get all of these values. So it was 52 minus 50 divided by 2.4. That's how we got our value. So we had our way of calculating our test statistic value, and we're just saying, look, the way that we decided near and far was with the p-value decision rule. So just look at that formula. It's important to kind of get a hang of what you're doing with that. Now, when we come to the regression, it's basically the same thing. We're using the sample to infer something about the population. But really the thing that we're interested in is whether or not the slope is 0. Okay, so our null is going to be that the slope is not different to 0. Our alternative is going to be that the slope is different to 0. Our test also is a t-test. So we're going to have a slope estimate and we're going to have a standard error estimate. So we're just going to call it the standard error. It's not the standard error of the mean anymore. It's the standard error of our test. So we have our decision rule, p-value less than 0.05. So what does this mean? It means that we have a sample of data, right? We don't observe the whole population. We have one sample of data. From that sample of data, we're going to fit a trend line. The trend line we fit is going to be the line that minimizes the sum of the squared error terms. What we want to know is, could the slope that we've estimated be due just to chance? Could it be that the true population slope is 0 and just random sampling error meant that I sampled in the way that I've shown here, and that I've estimated a slope of 0.27 when truth is that there's no slope? So what we want to guard against is we're saying, well, what can we say from this sample? Could this sample be drawn from a population where the mean is 0? So there is a slope effect or there isn't. So that's really the setup that we're trying to test when we conduct our statistical tests on the slope. So how are we going to set up our test? Our test is going to be that the null, the slope, is equal to 0. The alternate, the slope is not equal to 0. Alpha 0.05. We will be calculating a test statistic, but we are going to use the p-value decision rule, same one that we're always using to date. Less than 0.05, reject the null. Greater than 0.05, do not reject the null. How are we going to do all this? Well, it turns out that you've already seen this. So the LM model that we estimate is going to have all of the information that we need to conduct our t-test. So our statistical test of whether or not the slope is different from 0. All we need to do is when we save our output, apply the summary command. So you apply the summary to the object. The object is lmbird. What is lmbird? It is the linear model that I've estimated, which is going to have length explained by age. All right, and then we just draw some inferences. So what does this look like? So you can see up here, I've got my LM1 is equal to linear model, length, tilde age, data, wingspan, apply the function summary. It shows you the linear model that I estimated, gives me something about the residuals, and this guy here, the coefficients table. This is where our t-test is, so our t-value. So let me just zoom in on that for a moment and see, okay, we're interested in the slope coefficient. So in the coefficient section of the table, you can see that there's this slope estimate. This is the standard error. So this is directly analogous to the standard error of the mean, and it performs that same function, but it's over the estimate of the slope. Okay, so it relates to this guy. This is our t-value. So this is the test statistic, which we define as near and far from 0. And for us, we're going to use our p-value decision rule. So we just look over here and we're going to say the estimate of the slope, which is 0.27, is statistically different from 0. And that's based on this p-value here being much, much less than 0.05. So what I've got down here is, where does this t-value, so this guy is based on the t-value, where does this t-value come from? Well, it follows this same pattern that you've seen before. So we had the sample mean with the null hypothesis and the standard error of the mean. Down here we have our slope estimate, which is our sample estimate, our null hypothesis value. Actually, our null hypothesis value is always going to be 0 now, divided by the standard error of the slope estimate, which is reported, which is this guy up here. Okay, so you can see R is going to report all this information. The bits that we need are this guy, the slope estimate, and this guy, the p-value, to tell us whether they're different. And when you write your results table, you're also going to report this guy, the standard error. All right, but you'll see that in due course. So the regression model has a structure for its testing that is straight up what you've seen before. So no big deals here. So we're all okay. Remember this, how is this test statistic working? So just a reminder here of our t-distribution. So the rule of thumb that you've got is those t-values around 2. So you can see, when you've got a sample of 20, you're going to have a critical value of about 2. When you've got a sample from 100, it's 1.98. And in the limit, it's 1.96. Okay, so the critical value rule of thumb, t is different. The critical t is different for every sample size, but roughly, it's always going to be around 2, not too far from 2. So in our case, what does it mean? You have close to 0 is the do not reject zone, far from 0 is the reject zone. We could have big negative numbers for our critical t-value, or big negative or big positive numbers. It doesn't matter. It's just far from 0 is what's going to generate our result. So what do we have? We have our estimate of the slope, 0.27. The null hypothesis is 0. The standard error of the slope, 0.013. Plug all these values in. 27 minus 0 divided by the standard error gives us 20.3, which was the value that we saw in the regression output. We've got a sample of 11. Critical size would be 2.2. 20 is way up here, so we're way past the threshold. But of course, we can simplify all of this by just looking at the p-value decision rule. So rather than look at the t-distribution, we just look at the p-value. And so when we skip through to the results, you can see we look at the slope, then we look at the p-value. We can, base on that, say that the slope is statistically different from 0. that means that there's a genuine trend. The slope that we're observing is not due to sampling variation. We think that this is a trend that exists in the underlying population, and that's an opportune time for a break.